So where we left off in class was that we were talking about the harmonic oscillator, and we were talking about the harmonic oscillator in the energy basis, where basically we can write our Hamiltonian operator as the usual momentum squared operator over 2m plus 1/2 the mass, the frequency squared, times the position operator squared. And what I did at the end of class was to say, let's rewrite this. Let's write this now, not in terms of momentum and position operators, but in terms of an operator A, which I said was alpha times the position operator, plus I beta times the momentum operator, where alpha is the square root of m omega over 2h bar, and beta is 1 over the square root of 2m omega h bar. And then we can write the adjoint of that as a dagger alpha x minus I beta times the momentum operator. Okay, so it had some unique features. One of them, which we proved in class, was that the commutation relation for A and A dagger was just 1. And we could rewrite the Hamiltonian operator as A dagger A plus 1/2 times h bar omega. So I could write down something now called the dimensionless Hamiltonian. Where I basically divide out the operator by h bar omega. So I'm going to call that h bar hat, which is A dagger A plus 1/2. But like I mentioned in class, now this is kind of an intriguing solution, because we already knew from when we did the Schrodinger approach that the total energy is equal to some index n plus 1/2, and that whole quantity times h bar omega. So the energy of each energy level kind of fits with what the new Hamiltonian operator is. So we don't have the kind of complicated differential equation with x squared and momentum squared. Instead, we just have these two kind of unique operators, A and A dagger, which contain position and momentum, but in a much kind of more concise form, and in a form that looks like, and what we'll show soon enough, is an easy route from the Hamiltonian operator to the energy equation for that. Okay, so if I use the dimensionless Hamiltonian, let me go back. So if I take my Hamiltonian and operate on an energy eigen vector, that should give me the total energy like times the state back again. As an eigenvalue problem. Or I could write this now, if I divide both sides by h bar omega, I would have something which is more like the dimensionless Hamiltonian times a dimensionless energy eigenvector is equal to the dimensionless energy epsilon times that eigenvector back again. So all we're doing is kind of hiding the h bar omega, which is kind of like the base unit. And we can just hide it in the dimensionless quantities. And so, okay. So what I like to do is do a few more exercises with the operators A and A dagger. And one of them is, what if I take A and commute it with A dagger A? What would happen here? So before I solve this just by brute force, what I wanted to do was have a little bit of fun with commutation relations. So let's say that we have three operators. Omega, lambda, and gamma. And I'd make the commutation omega, gamma, omega and the combination of lambda, gamma, which is really omega, lambda, gamma, minus lambda, gamma, omega. So that's what the commutation, that's the definition of a commutator. But if I look at other combinations, the commutator of omega and lambda is omega lambda minus lambda omega. The commutator of omega and gamma is omega gamma minus gamma omega. Again, those are just definitions. But what we can kind of see is that what you kind of see here is I can come up with some different combinations that are going to kind of simplify things. So if I take this commutator, omega lambda, and then just multiply it by gamma, I should get omega lambda gamma minus lambda omega gamma. And if I take lambda and multiply it by omega gamma, then I get lambda omega gamma minus lambda gamma omega. So all I've done is take the commutator and then multiply it from the left by the operator lambda. Okay. So now if I take a look at this, I have a, let's see, I have a lambda omega gamma in both terms. And one is negative and one is positive. So really, if I add them together, so if I was to add basically lambda with a commutator of omega and gamma, plus the commutator omega lambda, which is then multiplied by gamma, then I should get omega lambda omega lambda gamma minus lambda gamma omega, with those other two terms canceling each other out, which, if I go all the way back to the beginning, was just what you get from the commutator of those two. So I can rewrite this identity now as one operator, omega, the commutator with a product of operators, lambda gamma, is equal to lambda times the commutator gamma, or omega and gamma, plus the commutator omega lambda with now the gamma on the right hand side. So what you're really doing is it's a distributive property. So I'm distributing the two operators in the product here, these two operators here, and I'm distributed them with the commutator. You can actually get a similar result if you put the product as the first argument in the commutator. So if I had omega lambda gamma, then that would be, if I distribute them, omega times lambda gamma plus omega gamma multiply with lambda. So if you have a commutator that is between one operator and the product of two other operators, then you can break up that product into basically, you can distribute it to other commutators. Okay, so that's going to make life a whole lot easier now. If we now go back to our operator A, which I want to operate with A dagger A, that product. So when we do that, if I now distribute it, I get A dagger times the commutator of A and A plus the commutator A dagger multiplied by A. Now the commutator of A in itself is just A minus A times A, which is 0. And we already said that the commutator of A dagger is 1. So it is an interesting result that the commutator of A and the product A dagger A is just equal A again. It's like an identity. Okay. So let's apply that now to further kind of commutation relations. So if I take the operator A and operate with the dimensionless Hamiltonian, then that's like taking the commutator of A and A dagger A plus 1/2. So with these commutators, I can break it up if there is a summation in there. So that would be equal to A dagger A plus the commutator of A and the number 1/2. So we said this first commutator we just worked out and said it was A. And this other one now is A times 1/2 minus 1/2 times A, which those two things cancel each other out, and we're left with A. So that means if I take the commutation relation of A with the Hamiltonian, the dimensionless Hamiltonian, I get A, that back again. So it's almost like a conservation property that if you operate with the operator A on that dimensionless Hamiltonian, you get the operator back again. Okay, now let's try it with A dagger. So if we take the commutator of A dagger with the dimensionless Hamiltonian, we get A dagger A plus 1/2. And that gives us the commutator A dagger A plus the commutator A dagger and 1/2. So this commutator is, if I work it out with the distributive property, A dagger A plus A dagger A times A dagger. Is that right? No. The dagger's here. Plus 0. The commutator of A and 1/2 with itself just cancels. And so what I get is, the commutator of A dagger A, that's 0. And so I'm left with A dagger times A dagger A minus A dagger, which is the same thing as minus the commutation relation A dagger, which is 1. So I get A minus A dagger. So the commutation relation of A dagger and the Hamiltonian gives me the negative of A dagger.